Hi, this is Kenny, and let's start off talking a little bit about waves. So the first thing is, what is a wave? Well, a wave is any disturbance in a medium. Well, that brings up the question, what's a medium? A medium is anything the wave happens to be traveling through. Like for my voice, if you're in the room with me, the air would be the medium. For ocean waves, water's the medium. So it's simply what the wave's passing through. And it's the medium that actually determines the speed of the wave. So sound in air will travel a completely different speed than sound in water or sound in a solid. And so the medium controls the speed of the wave, no matter what type of wave it is, at least as far as what we call mechanical waves. Different types of waves could have different speeds in the same medium, like the difference between light traveling in air versus sound traveling in air. Or the same wave could have different speeds in different medium, like, again, sound traveling through water or air or a solid, or maybe even sound traveling through different temperatures of air. That could make a difference on the speed of the sound wave. But in all cases, waves carry energy, not matter, from one location to another location. So waves carry energy. There are basically two classifications of waves. We have mechanical waves, and those are mostly what people think about when they think about waves. They're your sound, they're water, they're waves in a string if you shake a string up and down. Electromagnetic waves are all part of the electromagnetic spectrum. So that's your radio waves, your X-rays, your gamma rays, ultraviolet, infrared, visible light, microwaves. Any of that stuff are electromagnetic waves. And what's unique about electromagnetic waves is they're the ones that actually don't need a medium. They can travel through space, no trouble whatsoever, where sound cannot travel through space at all because there's not a medium for that sound to travel in. But for light, it's no trouble at all. Same thing with heat and with X-rays and ultraviolet. They carry their own medium with them. They all also have the same speed. And the speed of electromagnetic waves is a lot of times what we call the speed of light, which is 3 times 10 to the 8th meters per second. And we use it so often, we give it a special letter, lowercase c. So in the most famous equation of all times, E equals mc squared, that c is this number squared, where all electromagnetic waves travel at that speed in a vacuum. Another thing is, mechanical waves can be either type of wave, what we call transverse or longitudinal, which we'll get to in a second. But electromagnetic waves are always transverse waves. So what's the difference between these longitudinal and transverse waves? Well, a longitudinal wave vibrates along the same direction that the wave's traveling. So it looks something like this. If I take this slinky and I pull back one section and let it go, where that vibration is back and forth. I pull it back this way and let it go. That pulse that runs through, that is a longitudinal wave, where it vibrates in the same direction that it's moving. So it vibrates back and forth this way as it's moving in that same direction. That is a longitudinal wave. So it goes along the same direction it travels. A lot of times when we draw it, we either use dots or lines, or we try to make it look like a slinky. But it's going to have places where things are close together, where it's spread apart, close together, spread apart, closer together. In this type of wave, one of the best examples is sound. Think about a speaker. If you ever see a speaker moving, the speaker moves back and forth, presses and pulls back, presses and pulls back. Well, that sends out that pulse as it goes back. The push and come back, push and come back. We call it compressions or rarefactions. But one of the best examples of longitudinal wave is sound. But that's not the type of wave you normally think about. When you think about a wave, what you're really thinking about is what we call a transverse wave. A transverse wave vibrates perpendicular to the direction the wave is traveling. A longitudinal wave is parallel. Transverse is perpendicular. So it will look something like this, where it's vibrating up and down, like this. My hand's moving up and down as the wave's traveling sideways. That would be a transverse wave. It's going across the direction it's moving. And so that's the type of wave we normally think about when you think about a wave. When you think about a wave, you think about something that looks like this. If I can draw better, it looks something like that. Where this would be everything if it was perfectly still, but because we put that wave in it, we slap the water or we shake the string or something like that, we create this wave, and that's a transverse wave. In transverse waves, examples are like light. Any of the electromagnetic spectrum, so X-rays, gamma rays, infrared, ultraviolet, all those, but also water waves. The traditional waves that you see on the ocean, those are transverse waves. If you shake a rope up and down, you'll get a transverse wave. In our later video, we'll talk about the characteristics of these waves and what we can measure actually from the wave. All right, thank you and have a good day and good luck with physics.